For starters, maybe I'll enlist you guys to help me out on this stuff. Okay, let's start question one. Confidence interval for a parameter, or maybe you could say statistic, or for a parameter for mean, for a population mean, is constructed by adding and subtracting to a given point estimate, mean or proportion. Okay, that's your statistic. So what did I just say? Margin of error. I just gave you the answer, didn't I? Right. So the answer to that is margin of error. We're adding and subtracting. I can't believe I did that. We're adding and subtracting a margin of error to a point estimate, like a mean or a proportion that we got from a sample, in order to get a confidence interval. Now, the margin of error, of course, is some value for t or z, depending on the sample size, and if we know the population standard deviation, usually 1.96 for a 95% confidence interval, or 2.58 for a 99% confidence interval, or 1.64 for a 90% confidence interval, right? That number, that value for z, or as might be the case in a very small sample, t value, times the standard deviation. Standard deviation of population if we know it, but if we don't, pop the standard deviation of the sample. Okay, I think we're all okay with that, right? Okay, when a higher confidence level is used to estimate a proportion and all other factors involved are constant, does the confidence interval get wider, narrower, the same, so on and so forth? Got an opinion on that? We're increasing the confidence. We're asking for a higher confidence interval, going from 95% confidence interval to 99. So even without, should I wait for somebody to type in? Anybody want to hazard a guess? Yeah, it gets wider. Even just looking at it from the perspective of common sense, if we want to be more confident, we want to be 99% as opposed to 95% certain that the two numbers that the number range that we create, the lower and upper end of the confidence interval, will capture the mean. Well, we're more confident if the mean is wider, and we're less confident, say 95%, if the less confident if the range is narrower, and even less confident if we make it even narrower for a 90% confidence interval. But of course, that also relates to the 2.58, the 1.64, the 1.96 is really what determines how much wider and narrower for each confidence level. You're planning to use a sample proportion, p-cap, to estimate a population proportion p. A sample size of 100 and a confidence level of 95% yield a margin of error of 0.025. Okay, which of the following result in a larger margin of error? Well, you want to know something? There's a lot of, it's kind of a red herring, because we really don't need to know any of that stuff. We want to know which of the following four things would result in a wider confidence interval. So let's read this. Increasing the sample size while keeping the confidence level the same. 95% confidence, we get a bigger sample size. We are more confident it's going to be narrower, right? So this is going to make a narrower margin of error. So it's not one. Decreasing the sample size while keeping the same confidence interval. Well, that decreasing the sample size, remember that it's going to make a bigger standard of error because the n, square root of sample size, is in the bottom part of that equation for standard error. So this is actually going to make it wider. So that's going to make it wider. Increase in confidence level while keeping the sample size the same. Want to be more confident? Got to make it wider. So 2 and 3 both increase the confidence level. And decreasing confidence level while keeping the sample size the same. Again, if we're willing to be less confident, we can make it narrower. So it's really just 2 and 3 that would apply here. Okay, good. I'm glad you guys are. Why does decreased sample size make it wider? Okay, if we remember, the standard error is equal to the standard deviation divided by the square root of n. So the standard deviation is not changing, but the square root of n is going to be a smaller number. So when we divide a number by a smaller number than we would have divided it, then that overall fraction is bigger. Like if the standard deviation were 100 and the sample size were 100, it would be excuse me while I turn that thing off. It would be 100 divided by the square root of 100, the sample size, would be 10, so the standard error would be 10. Okay, but now let's see if I make that sample size smaller, say 25. Now I would be taking the 100 and divide the standard deviation of 100 and dividing it by the square root of the sample size, which is 25, and that'd be 100 divided by 5. So now it would be 20, right? So our standard error gets bigger. We multiply by 1.96. That whole margin of error gets bigger, and that means we're subtracting a bigger number and adding a bigger number to the sample proportion or sample mean, which makes it wider. Okay, does that make sense, Georgie? Did that help? Okay, good. If you need to, guys, you'll be able to replay this later on and kind of go back through it and either catch me in errors if I make them, email me if I'm making a mistake here somewhere, so I can correct it. And or you can like slow it down a little bit so you get a chance to parse it and really figure out what I'm saying. In a clinical test with 2,171 subjects, 1,214 show improvement from the treatment. Find the margin of error for the 95% confidence interval used to estimate the population proportion. Okay, so what formula? I'm gonna pull up a piece of paper here, and I'm gonna say to myself, okay, now I have a proportion. I have a proportion p cap, right? So how do I determine what that range is, and what that and specifically, how do I find out what the margin of error is for the 95% confidence interval? We know the margin of error is p cap plus or minus, and the margin of error is this whole number that's in here, and that's going to be 1.96 for a 95% confidence interval times the standard error. We know for a proportion, the standard error is equal to the square root of p times 1 minus p over n. Okay, now that's when we have a single proportion. We're looking at confidence interval. It gets a little more complicated when we're comparing, doing a t-test for two proportions, but not really much complicated at all. Okay, so let's take a look at that. What's it going to be? It's going to be equal to, well, let's see. First, I need to know what p cap is, right? Or what p is. P is 1214 over 2171. 1214 divided by 2171. So that's equal to 0.56. I'm going to call it 0.56. So a p is equal to 0.56. I'm not going to bother with putting in 0.56 there because I really am just interested in the margin of error. So standard error is equal to 0.56 times I think we actually worked this out once before. Somebody actually had a question about it. Now that I'm doing it, 0.44 over the sample size, which was, let's see, sample size is the sum of those two things, right? Which is, okay, 21. Oh, actually, it's sample size. It's not yes and no. The sample size is 2171. Okay, divided by 2171. Right? That the positives were the 1400 and 2171 was the total. That's how we got the proportion. So what is that going to be equal to? It's going to be equal to, bring the calculator back up. See, personally, I prefer to use Excel for this kind of stuff. It's a lot less awkward than these computer desktop calculators. Times 0.44 equals this, divided by 2171 is equal to this. And let's find the square root. And it turns out it's equal to about 0.01, right? So standard error is equal to 0.01. However, our margin of error is 1.95 times 0.01. Or in other words, it's equal to about roughly 0.02. That's roughly 2 times 0.01. Okay, so that's our margin of error. Okay, is that one of the choices there? Yeah, it sure looks like it. Here's one. So it would be that choice right there. Okay, 95% confidence interval for a population has a margin of error of 3.9. Okay, so the margin of error is 3.9. If the Sample mean is 54.6, obtained a 95% confidence interval. So we know we know the margin of error, and we know the sample mean is 54.6. So the margin of error includes the value of z or t. So we don't even have to worry about that. All we have to do is add and subtract 3.9 to 54. Okay, so 4 subtracted from that is going to be 50.6, and it's not quite 50.7. So 50.7, that's a possibility there. Now let's look at the upper limit. Add 3.9, the margin of error to 54 is going to be 58.5. Okay, 58. So it's going to be this second one. Okay, you guys okay so far? We're all in agreement on this so far? Okay, good. In 2011 and 2012, 16.9%, the confidence interval of 14.9 to 19.2. That's the proportion in the confidence interval report portion of 2 to 19-year-olds who are obese based on an Haynes survey. What is the point estimate of true obesity? What is the point estimate of true obesity prevalence among 2 to 19-year-olds in the U.S. based on this survey? Okay, so what's the point estimate for the level of obesity based on this sample? What's it going to be? Is it the 14.9? Is it the 19.2? Can you not determine it? Well, the point estimate is going to be in the middle, right? It's going to be like the mean, whatever the mean is, or what the proportion that the sample gives us. Now, notice point estimate. It doesn't say that that's the population proportion. It says it's a point estimate. In other words, an estimate based on this sample of the proportion in the entire population. So that's equal to that 16.9, which is what basically, because of the way it's calculated, it's adding and subtracting the same amount. The point estimate is always where it's the mean or the proportion, is always going to be in the middle of the confidence interval. Okay, so it's going to be 16.9. Interpret the 95% confidence interval. 95% confidence interval, 14.9, 19.2, looks familiar. Reported in the Journal of American Medicine article. Funny, said before it was a different source. Now you know we make this stuff up all the time, right? Okay, now note in the study, the confidence interval are not symmetric. This can happen. Notice in the study reported in the journal, the confidence interval is not symmetric. This can happen when the confidence interval computation are based on advanced methods. In other words, remember I just told you the way we do it, it's always going to be the same. It's going to be symmetrical. Well, in this case, it's saying, there was an advanced method used here. They don't specify what. And well, they do specify the method, but they're warning us that it's not necessarily symmetrical. Okay, in other words, the point estimate is not necessarily in the middle of this range the way it was in the previous problem. We are 95% confident that the obesity prevalence is between 14.9 and 19.2%. Well, even if it's not in the center, I still feel comfortable with that. The previous answer was 16. The previous answer was 16.9. Yes, right, because it's the middle of the confidence interval. I need to turn that off so it doesn't drive us crazy. It drives me crazy. Okay, I think that does it. Okay, that was an alarm to make sure we got started on time. Okay, so what about the second one? We are 95% confident that obesity prevalence is in the oh, look, we went back to that, is between 14.9 and 19.2%. I'm trying to see what is the difference here. That the obesity prevalence in the U.S. Oh, wait a second. Let's read the problem a little bit more carefully. Note that not symmetric. This can happen. And Haynes. This is based on a U.S. survey. I guess it was reported in the journal same way. This is based on a U.S. survey. Confidence intervals are not symmetrical. We are 90% survey. N Haynes is between these two. That looks right. 95% certain. You know, I'm trying to read what the difference is here. We are 95% confident that the obesity prevalence among 2 to 19-year-olds in the U.S. is between 14.9. We are 95% surveyed in Ed Haynes is between 14 and 9. And what's this third one? We are 95% confident that the obesity prevalence in the general U.S. population is between 14 less. Oh, actually, I have to. It's a little bit of semantics here. We are 95% confident that the obesity prevalence among the 2 to 19-year-olds surveyed in the N Haynes is between these two numbers. Well, no. We know exactly what the prevalence was among the children that were surveyed, right? The prevalence was whatever the middle it is. The survey was 16.9%. We know that, right? The confidence interval only applies to the population proportion. We are 95% certain confident that the obesity prevalence 19-year-olds in the U.S. is between 14.9 and 19.2%. That sounds plausible, right? Because we're estimating the range that we would expect the population proportion for this population 2 to 19-year-old. And then finally, this third one, we are 95% confident that the obesity prevalence in the general U.S. population, they forgot about the 2 to 19-year-olds. And I think we can eliminate none of the above because this first one seems valid to me. Right? Guys get why the difference is that one was in the U.S., the other was the N. Right, exactly. This one is actually not even they're not even talking about a confidence interval because we know what the prevalence was in the children that were surveyed. We know the exact prevalence, right? So we don't even need a confidence interval to say what this is. And this one, they're talking about the whole population. This is the only one that actually involves an estimate of a population, at least the population that we're really looking at. Okay. Suppose you wanted to investigate. That goes to show you, it's a lot of times it's easier to interpret the math than to apply it to some of these problems where you have to kind of interpret what analysis you're doing, what test you should apply, and so on and so forth. So a lot of times parsing these problems is half the battle. Suppose you want to investigate the obesity prevalence in New York City. How many 2 to 19-year-old New Yorkers are needed to ensure that a 95% confidence interval for this population will be within 2% of the true population obesity? I got a lot of questions on this one. Did you guys, any of you guys struggle on this one? Because you have to make a little leap of faith here, right? Okay, so let's take a look at this. Let's look at how would we calculate a 95% confidence interval for these 2 to 19-year-olds. Okay, well, again, that's going to be equal to, it's going to be equal to P cap, whatever the proportion is, plus or minus the standard of error. Well, in this case, we want to say it's going to be within 2%. Our 95% confidence interval will be within 2% of the true population obesity. So I'm assuming that's going to mean 1% on one side and 1% on the other side. You guys all agree with me on that, or did you interpret that as 2% and 2% on each side? Opinion? You guys have an opinion on that? No opinion? Okay. Okay, we'll be within 2% of the true population. Actually, I'm wrong. I think to be within 2%, 99% for this population, to be within 2% of the actual population. Okay, I'm gonna go with you. I'm gonna say 2% on each side. New York is made to ensure that the 95% population will be within 2% of the true population density. The only reason I feel uncomfortable with that is, let's say the true population density is 50%, right? if we had 2% on each side, then that would be 48% or 52%. Well, let's say that the true population proportion comes out to be 49%. Well, then 49% is more than 2% away from 52, right? So I think that in order to make sure, it's not a great question, is it? I might have to, if I put something like this on the test, I might try and clarify that a little bit or nail that down a little bit, but I'm going to go with what you suggested for starters, plus or minus 2%. So for 50%, it would have been 0.48, 0.52. So I'm going to have to add and subtract 2% from whatever the population proportion is. But I don't even really need to know that. All I need to know is that my margin of error is equal to 2%. So what does that mean? 2%, my margin of error is equal to, it's going to be equal to 1.96 times the square root of p times 1 minus p, right, over n. So that's what my margin of error is going to be equal to. So we want to make sure that that's equal to 2%. Your computation based on in class and our p is going to be a conservative value of 0.5. The reason why p 0.5 is a conservative value is because if you look at this standard error here, this p times 1 minus p, in order to make that number the biggest it possibly can be, p has to be equal to 0.5. 0.5 times 0.5 is equal to 0.25. Any other p-value is going to be smaller than 0.25. So for instance, if I had said 0.3 and multiply 0.3 times 0.7, that's equal to 0.21. So any other value than 0.5 is going to wind up making this portion of the margin of error a smaller number. So 0.5 is going to be the most conservative. Okay, 0.5 times 0.5, the top of this becomes 0.25. Okay, so now I have to find a way to solve for n. So the first thing I might do is get rid of this 1.96. I'm going to divide both sides by 1.96. Right? So we got rid of that on that side. Now, this is in a square root. So in order to isolate the n, I'm going to have to square this side and square the other side. They're both on either side of an equal sign, so they're equal numbers. So if I square them, they'll still be equal. So in other words, 0.02 divided by 0.02 divided by 1.96 squared. This thing will not stop. Is equal to, if I square this, I'm just taking away the square root, 0.25 over n. Okay, so now in order to deal with this, which is on, let's see, what's a good way to do this? Now I'm going to cross multiply. My goodness, this turned out to be a little bit nastier than I thought it was going to be. Okay, so now if I put this whole, actually I'm gonna solve this now, so make things a little easier on myself, right? So let's work that calculation out. Okay, 0.02 divided by 1.96 is equal to that. And I'm going to put that into memory. I'm going to multiply it by itself. And it comes out to be that. And I'm going to actually clear my memory. I'm going to put that into memory. So I have it to use. But it's equal to, this whole thing is equal to, whoops, made that go away, 0.0000104. Now I'm going to continue with this calculation. So this is of some interest to me. Is equal to 0.25 divided by n. Okay, so now I'm going to cross multiply. So it's going to be n times this value is going to be equal to 0.25. So n times 1.000104 is going to be equal to 1 times 0.25, 0.25. So now I'm going to divide by 0.000104. So let's figure out what that, and that's going to give me my sample size. N is equal to, okay, N is equal to, I'm going to clear, going to be equal to 0.25 divided by, now remember I put that number into my memory, okay, and that's going to be equal to about 2,401 people. Now, whenever we do a sample size calculation, we always round up because we want to know what sample size we need. So we need, if we choose 2,400, it'll be too small. So we need 20, and it's going to be equal to 2,401. Okay, now let's see how precisely we got that. Bingo, we got it right on the nose there. So I'm going to go with the assumption that Ellen was right, that the intent of the problem was to say 2% on either side. So a range of 4% that would capture I mean, if I were going to rephrase this question, I would make that a little bit clearer because I think it's possible to interpret that as 1% on either, a margin of error of 1%. So you have a range of 2% for that value. But I would kind of like probably try to nail that down a little bit better. In fact, if we had tried it 1% on either side, I think it would round up probably quite a bit larger. And I don't think that a value that would work for that would have appeared here. Okay, so now using the NC birth data, what is the 95% confidence interval for the percentage of low birth infants born in the state of California, North Carolina in 2001? Okay, well, if we look at the NC birth data, okay, and I want the SPSS version of this. See if I can catch a copy of it. Oh, that's a doc file. Here we go. Dropbox. I think it should open anyway. And I have SPSS started here, so it shouldn't take too long for it to come up. I'll give it a moment. Otherwise, I'll wind up going back and looking for it again. Let's try it again outside of Dropbox. Oh, that seems more promising, right? Let me get rid of this version. Oh, no, I don't want to do that. Why does it think that's the last data editor? Okay, I'll open it from here. Open, data, and oh, here it is. I lucked out. I don't care about that. Okay, so let's take a look at what we have here. So we have one of the variables here is low birth weight babies. Okay, and for that variable, low birth weight babies, so welcome to the club here. I hope this is not really true. I don't know why it's saying that. Okay, for the low birth weight babies, I go into the variable view. If I look at low birth weight babies, the value 0 equals not low birth weight, and 1 value equals low birth weight. So we're interested in that particular variable. So I'm going to analyze, and I'm going to go down to descriptive statistics, and I think crosstabs. I'm going to give crosstabs well, maybe not. Let me think here. Which ones do I want? You know, I don't remember having done this in a long time. I think analyze, descriptive statistics. How about frequencies? Maybe I can find out from frequencies. Let's take a look at the number of low birth weight babies in SPSS in terms of frequencies. Low birth weight babies. See what I get from frequencies. Well, the frequency tells me that the percentage of low birth weight babies was 8.8. Okay, now I want to determine a confidence interval for that proportion, 8.8%. Okay, and analyze statistics. I'm going to go to explore, see if this allows me to do this. Usually I don't bother using SPSS for this. Low birth weight babies, statistics. Okay, confidence intervals. Let me see if it'll run this for just that. Okay. Okay, and the mean was 0.09 for low birth weight babies. The mean number of low birth weight infants was 0.09 with a confidence interval of 0.07 to 0.11. Is that one of the selections that we have there? I just want to get this resolved so I know that I'm doing it correctly before I cast this on. 95% confidence interval is 0.07 to 0.01, and I'm going to have to look the answer up. Let me go into Blackboard, check the answer. Okay, log in, log in. Okay, assignments. Okay, let's edit this. We'll go down there and get the answer. That was problem number 9, right? Problem number 9. Oh, no, problem 8, 9. Yep. Jeez, this thing will not stop ringing. Let me make sure that this is, that's definitely turned over. Okay, so the 95% confidence interval is between 7 and 11%. Let me just quickly go back over that so that without the little glitches and stuff like that, so you guys can see what I actually did there. I have the data open for an SPSS. This is the data for the North Carolina births. The variable, a categorical variable, because basically a proportion is basically the two sides of a categorical variable, the percentage of children that were ones, but low birth weight versus the total number of children, right? So I can go into frequency, analyze, descriptive statistics, frequencies. If I'm just interested in, I moved low birth weight in here already. If I'm only interested in knowing what the proportion of low birth weight babies is, I can just go in there and it'll tell me, well, the proportion is low birth weight babies is 8.8% out of the total. Okay, there's 800 children total, 70 of them were low birth weight babies. Turns out to be 8.8%. Okay, so now I can also, if I want, let me see if I can also use frequencies. Let me see if there's any options in frequencies. What else means? No, I'm not going to do that. Okay, so now if I want to know, if I want the 99% confidence interval, I'm going to go into Analyze, Descriptive Statistics, Explore, and that's going to give me the opportunity to move low birth weight babies in here. I'm not going to move anything into the factor list because I'm only looking at that one variable all by itself. In statistics, it's already set up to give me a confidence interval for the mean or the central value. And I'm going to say, okay, let's get that value. And it's going to give me a new table, which tells me that the mean is 0.09. It seems like it rounded it up, 100%. Case summary, median would be 80, rounded to 0.09%. It's giving me 2 decimal places after the mean. So 0.09%, and the range, the lower confidence interval is 7%. The upper confidence interval is 11%. I would be more comfortable doing that in Excel myself. I'm not even sure why we would be using Excel to do that, but I mean SPSS to do that. If I see a better way to do this, I'll bring it up on over the weekend when we have another review session. Yeah, I'm not in love with using that method here. Okay, so anyway, let's go to the last one. Using NC birth data set, answer the following question: 95 for the mother's mean age in years for infants born in North Carolina State in that following year. Okay, so we want the confidence interval for the mean age of the mother. So, okay, let's go back to SPSS. Okay, let me get this out of the way. I'm back in SPSS. Okay, and I'm going to look for the data window. Okay, so let's see, where's the mother's age? Here's the mother's age right here. It's a numerical variable. So I'm going to calculate a mean. I'm going to go to Analyze, Descriptive Statistics. I'm not going to use frequencies because frequencies is used for category variables. Males, how many males there, how many females, how many low birth, how many normal babies, and so on and so forth. So I'm not going to use that. I could go into Descriptive Statistics, or I could go into Explore. Let's do both. I'm going to go into Descriptive Statistics first. I'm going to ask it to find, let's see, options. It's going to find the mean, standard deviation, minimum, maximum, range, variance. So what is it? What's missing here that I should be after? Anybody want to tell me what I'm missing here? What the problem's asking me for? I don't have the confidence interval there, right? So I'm going to say cancel that. Okay, and instead of using descriptives, I'll cancel this. I'm going to go back, analyze, descriptive statistics. I won't use frequencies. I won't use descriptives. I'll use explore. And I'm going to move the mother's weight into the dependence list, into the number that we're going to analyze. Move the mother's weight in here. Okay, make sure that the statistics are set up for a confidence interval of 95%, which is the default. I'm going to click OK, and it's going to come up with the average age for the mother, which is 26.92, and the 95% confidence for the true mother's mean of all the mothers in North Carolina State at birth, at birth of the infant, 26.49 and 27.34. Okay, and you would fill those in to get the right answer. Okay, so you guys comfortable with that? We'll move on to the, I think that was the last question, right? We'll move on to the assignment. Comments, complaints? Are we pretty clear on that? Okay, good. All right, let's move on to the assignment. Preview, I think this is the assignment. Okay, let's take a look at this one. Let's go through this. Sample size of 100 has a mean of 160. Assuming the population is normally distributed with a standard deviation of 30, calculate the standard error for the distributions of sample size 100. So what is the standard error equal to? The standard error is equal to the standard deviation over the square root of the sample size. In this case, we don't have to worry about the standard deviation of the sample. We know the standard deviation of the entire population. So the standard error is equal to 30 sigma divided by the square root of the sample size, which happens to be 100, which is 10. 30 over 10 means that it's equal to 3. Okay? 30 over 10 is equal to 3. Enter the lower bound of the 95% confidence interval. Well, since we know since it's a large sample and we know the population standard deviation, I'm going to use the value for Z, not the value for T, right? So the value for Z is going to be equal to 1.96. I'm going to use 2 to keep things moving, right? So the margin of error is going to be equal to 2 times the standard error 3. So it's going to be the mean plus 6 and the mean minus 6. So the lower bound is going to be 160 minus 6 is going to be 154. Okay, and the upper bound is going to be 166. Okay, let's move on from that. Okay, enter the lower bound, okay, of the 99% confidence interval. Well, the only difference there is standard error is still going to be 3, but now instead of using 1.96, we're going to use 2.58, right? So 2.58 times 3, 2.58 times 3. My margin of error now is going to be equal to almost 8. I'm going to use the number 8. for our purposes here. So the lower bound is going to be 160 minus 8, or 152. It's actually just a touch more, and 168. Okay, again, I'm rounding. Remember, your answers might be a little bit different because I'm rounding. Okay, observing 36 randomly select. Now we're changing to a different problem. Okay, observing 36 randomly selected caseworkers, the supervisors noticed that an average number of cases carried by each worker in a week was 50. These people are overworked. I can tell that right away. From the previous long-term observation, it is known that the standard deviation, sigma, for the entire department is 9 cases per week. So we know what sigma is here. We're going to be working with the z. Calculate the standard error for samples of size 36 for this study. So the standard error, again, is equal to sigma, which we know is 9, right? We were given that, divided by the square root of the sample size, which is 36, okay, and that would be 6. So 9 divided by 6 is going to be 1.5, right? So the standard error is going to be equal to 1.5. Enter the lower bound of the confidence interval for the mean caseload. Well, now we need to calculate the margin of error. The way we calculate the margin of error is going to be equal to 1.96 times the standard error. Okay, 1.9, roughly 2, so it's going to be roughly 2 times 1.5, or 3. So we're going to add 3 and subtract 3 from the average number of cases, which is 50. So it's going to be 47 to 53. Okay, what about the 90% confidence interval? Well, the 90% confidence interval, once again, the standard error stays 1.5, but now I'm going to multiply by a z-score that represents a 90% confidence interval. Anybody remember what that t-score is? Z-score, rather, is, because we know that it's a large sample, and we know it's rather, not because it's a large sample, but because we know the population standard deviation. Anyway, right, 1.64. So 1.64 times 1.5 is equal to 2.46. I'm going to call it 2.5. So I'm going to add and subtract 2.5 to our 50 cases. So that's going to be 47.5, and it's going to be 52.5. Okay, now, quick question. 52.5. My 90% confidence interval. I think I made a mistake here. I definitely made. Did I make a mistake here? Enter the lower. Oh yeah, I'm sorry. I did not make a mistake here. Okay, so my 90% confidence interval. Do I expect that this is narrower than my 95 or wider than my 95? Right? Narrower or wider than my 95? Well, if I'm willing to be less confident, I can afford for my confidence interval to be narrower. I can have a smaller range and have that level of confidence. So what did I get? 47.5. And before, I got 47 to 53. So indeed, if we want to have a higher level of confidence, we have to have, and numerically it works out this way, but we understand that we also intuitively have to have a wider range of numbers to have a higher level of confidence. So the 95% confidence interval has a wider range than the 90% confidence interval. So it actually worked. We saw how it worked out in the math. Okay, we would like to estimate the mean amount of money spent on books by 100 college students, followed 100 randomly selected students. The mean spent was 249. Standard deviation of the sample is 30. Assume that 30 is a good approximation of standard deviation spent on all of them. So they're saying, let's assume that 30 can represent sigma. So we work with z rather than t. Okay, so a lot of these problems are going to be z. So I'm going to be posting another assignment due for the night of the exam, where I'm going to force you to use the t-values and the t-test. We're going to review that also on the weekend. Calculate standard error for all student purchases, book purchases, and it's equal to 100. Well, sigma is 30. 100 divided by the square root of 100 is 10. So 30 divided by 10 is going to be 3. Comes out the same as the other problem, right? Okay, what calculate margin of error for all student? So the margin of error is going to be 1.96, or 2 times 3 is going to be about $6 is our margin of error. And what was it again? 249. So we're going to subtract 6 from 249, which is going to be 243, and add to 249, it's going to be 255, right? And that's going to be a 95% confidence interval. Okay, next, a random sample. How many more do we have? Okay, just want to get a picture of what we're doing here. A random sample of nursing homes is taken. N is equal to 100. The proportion of patients with private insurance in this population is 35%. Based on this sample, calculate the 95% confidence interval for the proportion of nursing home patients citywide who have private insurance. Okay, so sample size is 100. The proportion of patients who have private health insurance is 0.35. The standard error for a sample size of 100 for this group is going to be 0.35 times 0.65, p times 1 minus p, right, divided by 100, and find the square root of that. Okay, I'm going to do that. So it's going to be equal to, let me clear everything, 0.35 times 0.65. I saw a question there, I'll get to it in a second. Divided by 100 equals this, and I'll find the square root of that. So it's equal to 0.05, roughly 0.05. I'm going to call it 0.05. So standard error for population is 0.05. Okay, a standard error in the population. I'm sorry, it's actually going to be this value. So it's not a fill-in problem. It's 0.048. Okay, calculate the lower limit for the 95% confidence interval. Well, again, we've multiplied that by 1.96, so we're actually adding and subtracting about 10%. So we'd be looking at 25%, and adding 10%, 45%. Okay, for this particular population. Okay, let me look at the question here. Regarding question 11, even if we were not told that the sample standard deviation is a good estimate of the population, so we could use these based on the fact, yes. The answer to that question is yes, because it's a large sample. For our purposes, if it's 50 or larger, you can use the z-score sample size. Now, just between, now keep in mind, if it's a proportion, one of the rules is that you gotta have to have at least 50 in each side of the proportion, 15 in each side of the proportion. For the most part, any proportion problem that satisfies that, in other words, has a sample size bigger than 30 for proportions, you can use the z also. Okay, so just for that, just for our purposes. Okay, but yes, anything 50 or larger, I would say you can assume that you know sigma. Okay, so let's look at this last one. I'm used to saying 30 most of the time, most semesters. I say 30. I noticed in the text or somewhere else that we've been working with, they define the large sample as anything 50 and above. So I want to keep it consistent. But if I say 30 by mistake every once in a while, it's because most of the time I've been using that to define a large sample size. Keep in mind that a lot of this, when we talk about large or small sample sizes, whether we satisfy that or not, it's kind of a moot point, because in real life we'll be using statistical software like Spss, which is always going to use t, a more accurate value, even if it's a large sample size. Because t is always going to be a little bit more accurate than just falling back to z, which really represents as a infinite sample size. Okay, so sorry I even brought that up. Researchers examined and Haynes to estimate the dietary of 10 ingredients. One of those nutrients was calcium. With intake measured milligrams for 60 years or older, found a standard deviation of 554. A random sample of 1,000 younger adults was found to have an average intake of 1,200 milligrams per day. Calculate the standard error for this sample of 1,000 younger adults, assuming the standard deviation of this population is the same as the older population. So only thing here is that we know the sample size, which is 1,000. We know the average, which is 1,200. And we're going to assume that we know sigma, which is 554. Again, sample size is very large, so we probably would have assumed that anyway. Okay, calculate standard error. Standard error is going to be equal to sigma. divided by the square root of the sample size. I wish that had been a nice round number, but it isn't. Okay, so it's going to be 454 divided by, 1,000. First of all, let me clear this out. 1,000, I'm going to take square root of 1,000. Okay, and it's 31.6. I'm going to put that into memory. Clear this. I'm going to take 454 and divide it by the square root of 1,000, which is that. And it comes out to be 14.4. So the standard error is equal to 14.4. Okay, so now calculate the lower limit of 95% confidence interval, 1.96 times the, I'm going to call that 15. If I call that 15 for our purposes, right, I multiply that by 1.96 or 2, comes out to 30. So I'm going to subtract and add 30. I'm going to subtract and add 30 from 1,200 milligrams. Okay, so it's 1140 and 1260. Oops, 1140 and 1260. Again, round it off. You wouldn't probably need to do this more accurately for it to automatically grade correct when you do it otherwise in the actual homework. Okay, before I close this up, is that clear? Are there questions on that? You always remember, you can always have a shot to go back and take a look at this again and see if you're confused about it, see what you have to do to kind of get straight with it. Okay? I'll wait for some responses there to make sure that like everybody's at least somewhat comfortable with this. Okay, I'm going to move on then. Thanks, Georgie. I appreciate it. Okay, so now I want to look at this idea of t-tests. Okay, one of the things that I want to remind you of is that when we calculate confidence intervals in t-tests, usually we're doing it because we want to understand what the true population proportion is. We're not really that interested in what the sample is. We want to know that point estimate, that middle value for a numerical value. Look, we want to know mean. For proportion, we want to know RP, right, and so on. And very often we want to know that so we can compare it to another population and try to demonstrate that there's a difference between the two populations. Okay, for whatever reason. One might be because we want to prove the drug works, or another might be because we want to prove that one population behavior or nutrition or something else makes a difference versus another populations of different nutrition and so on and so forth. Okay, so very often we're doing hypothesis testing, and often that hypothesis testing takes the form of a t-test. Okay, so I just want to show you these formulas again. Okay, now notice there's a lot of different versions of this t-test. And when we do a t-test, we're calculating either a t or a z value, right? Depending on sample sizes and so on and so forth, we'll calculate either a t or a z value. When we calculate a z value, things are usually pretty straightforward. When we calculate a t value, things can get a little bit sloppy, okay? So because the value of t that we have to exceed is dependent on the sample or degrees of freedom. Okay, sample size or degrees of freedom. Now, when I'm doing these different hypothesis tests, I can wind up with a lot of different situations. For instance, I can wind up with a situation where I have a single sample that I've taken and I want to compare it to a specific value. That is a single sample t-test. In a single sample t-test, what you're doing is you're taking the mean of your sample, you're subtracting, you're finding the difference between it and some value that you want to compare it to, like a known mean of another population, right? X bar minus, say, 100 or something like that. Dividing it by the standard error. What's the standard error? The standard error is the standard deviation. And if you don't know what it is for the population, it's the standard deviation of the sample divided by the square root of the sample size. So that t value is what gives you the number of standard errors apart. And if that t value exceeds the critical value that you need in order to say that there's less than 5% chance of that big a difference being due to chance, you can reject your whole hypothesis that your sample population is equal to the number that you're comparing it to. That's a single sample t-test. Paired sample t-test is really the same thing, except that you're comparing your mean to zero, the value is zero. Now, to understand that, you have to understand what a paired sample is. I'll get to that. If I don't get to it tonight, we'll get to it, over the weekend. But that you're really doing the same thing as single sample t-test when you do a paired sample t-test. Trust me on that for a moment, but we'll get to that. Okay, now, very often what you wind up with is two samples. Back, probably I could argue most of the time, you're working with two samples. And when you work with two samples, you're going to find the mean of one sample, the mean of the other sample. Now, your first sample is going to have, the sample from your first population is going to have its own standard deviation 1, let's say. Okay, your second population, your second sample, is going to have its own mean and standard deviation, say mean 2 and standard deviation 2, right? So now things get a little complicated now. So we're going to use the same format. The t-score is going to be equal, number of standard errors apart, going to be equal to the difference between the two means that you calculate from your sample divided by the standard error. Okay, now our standard error is down there, right? Now, problem now is that we have two standard deviations. One is a standard deviation that came from sample 1. The other is a standard deviation that came from sample 2. Well, in that case, what we want to do is we have to make a judgment. Are the variances of these two groups, are they equal or are they unequal variances? Very often, if we're measuring, say, the blood pressure of people in the Bronx and blood pressure of people in Brooklyn, we may find a difference in the average, but we may find that, the variability is the same. The averages may be different, but the variability in the numbers is the same. So we may want to assume equal variances. On the other hand, we might find that the variances are unequal. Variances or standard deviations are unequal. As a rough rule, if the variance of one group is less than twice the variance of the other group, or if the difference is bigger than twice as big or half as big, right? If it's less than that, if it's closer than that, we would assume equal variances for our purposes. If the differences are twice as much, like in other words, the standard deviation in one group is 10, standard deviation in the other group is 23, then we might be prone to assume unequal variances. When we do that, we change the way that we calculate the degrees of freedom and the standard error. Okay, so, and this is how this is going to work. So T is going to be, as usual, on the top here, the difference between the two means. But then on the bottom, for equal variances, we're going to use a pooled standard deviation, roughly something that really is basically kind of a weighted average. And that's going to be calculated by pooled standard deviation, going to be the sample size minus 1 for the population 1 times the standard deviation squared, that's basically the variance, plus sample size 2 minus 1 times the standard deviation squared for the second sample, all of that over the two sample sizes added together and subtract 2. So all of that, if I screw it at that whole thing, that all goes down in here for the pooled standard deviation, and it's multiplied by the square root, instead of being over the square root of n, it's actually over the square root of n1 plus n, 1 over n1 plus n, 1 over n2. So it's pooled standard deviation times the square root of 1 over sample size 1 plus 1 over sample size 2. You would combine these two fractions and then find the square root of it, and then now keep in mind that these are in the denominator, so it's going to be a little bit complicated doing this. You might do it on your calculator, just as decimal fractions to make it easier to add. So times the pooled standard deviation, and then we would calculate what t is. Now, in order to compare t that we calculate to the critical value of t to decide whether or not to reject the null hypothesis, we need to know a degrees of freedom. In this case, the degrees of freedom is going to be the sum of the two sample sizes minus, I think that should be minus 2. You know, I was I'm having a senior moment here. I'm gonna have to check that. Anybody got a one of the other references handy? Is that minus 1 or minus 2? I have a bad feeling about that. Anybody know? Maybe we're going to, well, you want to know something? It's such a small difference, probably doesn't matter anyway. But I'll check that also and get back to you. But let's say n1 plus n2 minus 1, that is our degrees of freedom. So if a sample size in each is 100, it would be 200 minus 1 would be 199. Basically wouldn't make much of a difference in the value of critical value of t. Right? So we would then compare what our t-value is to our critical value of t to decide whether or not we can reject the null hypothesis. Okay, now what about unequal variances? Unequal variances, again on the top it's the same, the difference of the two means, but the standard error is going to be calculated. It's actually a bit simpler. It's the standard error for the first group squared over the sample size for that group, plus second group squared over the sample size for that group, and then those two fractions added together and the square root of that whole thing found, and that gives us our t-value. Simpler, it's actually simpler unequal variances than equal variances. Unfortunately, the degrees of freedom is quite a bear to calculate. So it's so complicated and difficult that very frequently what people will do is take whichever one of these two sample sizes, n1 or n2, is the smaller, and subtract 1 from that and use that as the degrees of freedom. It's kind of like a gross overestimate of what, underestimate of what the sample size should be calculated to be, which is a very conservative outcome. Okay, so which is a good thing also sometimes. So for instance, if sample size 1 was 100, sample size 2 was 100, then for degrees of freedom we could calculate this, or for our purposes just say the degrees of freedom is the smaller one, the same, so 100 minus 1, or 99. Okay, so, and then finally, the last thing we come across is when we compare two proportions. When we compare when calculating confidence interval for one proportion and doing it kind of like a single sample t-test, where we might be comparing it to some fixed number, we use p cap divided by the square root of uh, uh, p times 1 minus p over n. When we have two proportions, for instance, if I want to know what is the difference in the mortality rate for women over 70 years old in population A versus population B, and the proportion of fatalities in population A was 2% per year, per decade, or something like that, and proportion in the other population was 4%, well, then the difference between the two of them would be 2%. That would be just like subtracting one mean from another. But then the standard error on the bottom would be based on both proportions, a pooled proportion. Like in other words, if there were 500 fatalities in one group, 500 in the other group, and that would be 1,000 fatalities. And if the sample size in the first group were 10,000 and in the second group were 10,000, that would be a sample size of 20,000. So I would add together the fatalities, divide by the total number in both groups, and I would get a pooled proportion, right? Which, if the sample size is the same, is actually halfway in between these two, right? So I would use that pooled proportion. That's what p-cap without a subscript is, the pooled proportion for all the people in the study in both groups, right? Times 1 minus the pooled proportion times 1 over the sample size plus 1 over sample size, and we would calculate what that value is. Notice with proportions, we're always working with the z-score instead of the t-score. Okay, so you can actually call this t and just compare it to 1.96 to decide whether to reject the null hypothesis, or you can actually take advantage of this and look up an actual proportion percentage. Okay, so now we've been working a long time, but I want to get into at least a couple of these. So for instance, I'm going to start with a single sample t-test. I'll open this up in Excel. Okay. Okay, so here is a population that I have in Excel. We probably played with this before, so you've probably seen it before. Okay, so the mean of this group, of this sample, is 10. The standard deviation of this sample is equal to 2.73. Now the standard error is going to be equal to, we don't have the population standard deviation. So the standard error is going to be equal to, the standard deviation divided by the square root of the sample size. And the sample size is 2, 4, 6, 8, 9, which is 3. Okay, and that's going to be equal to that. Now, I can calculate, let's say that I'm interested in comparing this to a population that I know for sure. That population I know has a mean of 13. That's mu. That's a population value, right? Let's say I know mu for that population is 13, and I want to compare our sample population to our known population, a second known population. Okay, that's a single sample. We have one sample, we're comparing it to a known mean of a different group. Okay, so how am I going to do that? Well, it's going to be equal to, I'm going to calculate t, right? It's going to be equal to, the difference between the two means, x bar minus mu. I could put mu in, or I could just put 13 in. Doesn't matter. It's the same thing in this case. Divided by the 1.9, divided by the standard, the standard error. Okay, whoops. Divided by, actually I should do this. Here, I need to put this in as a formula, is equal to x bar, which is 10, right? 10 minus 13 over the standard error. Okay, and now I'm going to go in here and edit this so I make sure that it does this subtraction first. And when we can enter, and it comes out to a t-score of minus 3.2. There are 3.2 standard errors between the number 10 and the number 13. Okay, so for a t-score, for a sample size of 9, I have our number of degrees of freedom is equal to 8. So if I pull up my t-table, I know I got one here, I just got to find it. If I pull up my t-table, no, don't have it there. Oops, it should be in here. Where did I put my t-table? T-table. I know I got it. There it is. If I pull up my t-table, the critical value of t for a sample size of 9, 8 degrees of freedom is 2.3. Well, since I just calculated that my t-score is equal to 3 something, I can reject my null hypothesis. Remember, my null hypothesis is going to be that the mean for population 1 is equal to the mean for population 2. And my alternative hypothesis is that they're not equal. I can now reject my null hypothesis. Single sample t-test. How do I do that in SPSS? Let's open up SPSS. I'm going to take the same example. Open. Data. Okay, and I'm going to go to the desktop. Oops. And desktop. And I'm going to go into, where was it, t-tests. Single sample t-test. I think I have same data in there. Okay, same data is there. Okay, and I'm going to analyze, compare means, one sample t-test. Simple enough, right? Okay, I'm going to move my variable x into that test variables. In options, going to do 95% confidence intervals if I wanted. But I'm going to compare it. What was the mean of the other group that I compared it to? Anybody remember? It was 13. I'm going to put that right in there. And it will calculate a t-score for the difference between the mean for my sample and that known mean 13. Okay, let's see if we get the same number. Well, indeed, we get our t-score is negative 3.286, 8 degrees of freedom. Our significance is 0.011, which is less than, that's our p-value, probability of being wrong if we reject the null hypothesis. That's the area of the tail to the left of negative 3.2 and to the right of positive 3.2. It's the sum of those two tails, right? That's two-tailed hypothesis. Okay, and that comes out to be 0.01. So since it's less than 0.05, again, I can reject my null hypothesis. Okay, so now, just to show you quickly that we also have data here for a two-sample t-test. Okay, and I got two versions of it. One version of the two-sample t-test that I have here. Okay, here's my two samples. Okay, one version of this, I'm going to calculate standard deviation and mean for these two groups. Average for this group is equal to that value. The average for this group is equal to this value. Now, what about standard deviations? For this group is equal to 2.7, and for this group is equal to 1.94. You know, they're not. One is not twice what the other is. I might use the formulas that we have outlined before for equal variances to figure out what the standard error is and to figure out what the degrees of freedom. I might use that for this particular problem. Okay, I'm going to put this away for now. We'll bring it back up over the weekend. We'll try it again. Let's take a look at this other example that's an Excel file. And I'm going to do the same thing. First, I'm going to make it a little bit bigger so you can actually see it. Okay, so let's see. Equals average, parentheses, and the average for the first group is equal to that, and the standard deviation is equal to this. And actually, you know what I should have done? I'm going to insert the rows so it makes it a little easier to see. And I'm going to do this. I'm just going to copy that to the right. To the right. Okay. Well, and you want to know something? My intention was that at least one of these sets of data would have different standard deviations that were so different that for instance, that this one, for instance, we would analyze. I'm not sure where I came. I'm not sure if I used the right data, if I pulled the wrong files out from somewhere else. But I was hoping that this one would turn out to be, let's say, whoops. Let's say this one came out to be 1.0, right? And well, the difference in these two standard deviations, one is more than twice what the other is. So this one, I would use the formulas for standard error and for degrees of freedom that are intended for unequal variances. Okay. Now, in either case, I can do my work on Excel and do my calculations using those formulas on that table, or I can go into SPSS, which I'm going to do right now. I'm going to say open data. And in this case, I'm going to look now at two sample t-tests. This happens to be the first one. It opens it up. My null hypothesis is going to be that there's no association. Gender, see, gender one represents male, two represents female, perhaps. Let's see, one is male, two is female, right? And this is the value for the males and the females. This is the way. Notice SPSS organizes the data in a slightly different way. The variable has to be all the gender variables have to be in one column. All the actual numerical variables have to be in the other column. Okay, so I'm going to calculate. I'm going to analyze this. I'm going to say analyze. I'm going to say compare means. Well, it's no longer a one sample t-test, right? Now it's a independent samples or two sample t-test. So I'm going to move the test variable into my numerical variable. Notice it got it wrong. This should be a numerical variable. It should be a little ruler there instead. Hopefully it'll work. It'll work anyway. I'm going to move gender into a grouping variable, and they'll tell SPSS that one represents one group, two represents the other, male and female. Okay, so I'm going to click OK. First, 95%, good. I'm going to click OK, and let's see what SPSS gives us. SPSS tells us that the mean of one group is 10, the mean of the other is 7.56, same as we found. The standard deviation of one group is 2.739, of the other is 1.944, same as we found. So it found the same values that we did. And then what it did a t-test. But before it did a t-test, it used these first four boxes. See these first four boxes? See how they're separate from the rest of this? That's a test for the equality of the variances. It works just like any other hypothesis test. The hypothesis is that we're starting assuming S1 equals S2, that the two variances are equal to one another. Okay, so that's our assumption. And in order to reject that assumption and go down to the lower row that the equal variances are not assumed, we have to find a p-value or probability of being wrong if we reject the null hypothesis of less than 5%. Well, the value, the statistic it calculates happens to be called F. No association with a different statistic. Don't worry about it. Okay, but the significance, the p-value, probability of being wrong, is 0.245. That's greater than 0.05. So I failed to reject the null hypothesis. So I stay in the top row. I assume equal variances. Well, if I assume equal variances, the t-test comes out to be 2.184. And how is that calculated? It's 10 minus 7.56 divided by the standard error. Somewhere in here, you actually see the standard error calculated. Comes out to 2.184. 16 degrees of freedom. How do we get that? 9 and 9 is 18. Oh, you know, it is minus 2. Right? Remember we looked at that chart before, right? SPSS actually took N1 and N2, added them together for equal variances, and came up with 16. 18 minus 2. So that should have been a minus 2. So remember that. Okay, I'll correct that in the meantime. Okay, so the significance, the p-value, the tails at the end of the distribution of samples, to the percentage to the left of 2.18, negative 2.184, and positive 2.184. When you add those two tails together, they come out to 0.04. So the probability of my being wrong if I reject the null hypothesis that males and females have the same mean for the populations is 0.04, which is less than 0.05. So I can reject the null hypothesis. Okay, so I don't want to beat this to death too much, but notice if I had assumed equal variances, that the t-value would have been very much the same. One difference, though, is our degrees of freedom is going to be different. Remember, that was a very complicated calculation for degrees of freedom if you assume not equal variances, right? And it actually affected our p-value, made it bigger. That degrees of freedom made it 0.046 instead of 0.044. We still reject the null hypothesis. It would have been a little bit closer, but we still reject the null hypothesis. No matter which one of these two assumptions that we made. Okay, so I'm gonna, there's one other situation which I want to show you very quickly, and that's paired samples. And I'm gonna go to paired samples in Excel, just to show you what it looks like. Let's say that you have a person, this instead of being two groups, like one group of people, a second group of people, this is actually one group of 9 people. Okay, and we had the people take a placebo, and we had them take the drug, right? So it might have been in the actual study, it might have been random. This person might have taken the drug first, and the placebo second. This one might have been placebo first, drug second. So we randomized that. But let's assume that we're looking at this as a result for both people. So let's see what the effect of taking the drug over the placebo is. Well, for this person, it made no difference. 6 minus 6 was 0 difference. Well, how about for everybody else? Well, I'll calculate that. Well, for this person, it increased the value by 12. For this person, it reduced the value by 6, and so on and so forth. I messed up by clicking in. I kind of messed up the direction, but that's okay. It doesn't really matter to us. So now, instead of trying to evaluate whether or not the drug was greater or lesser than the placebo, what we do is we now just look at the differences. The average difference for all of these people The average difference is 1.5. So now what we're going to test is that value of 1.5 statistically different enough from 0 for us to reject the hypothesis that there is no difference between the placebo and the drug? Is 1.5 different enough from 0? Okay, so now what have we turned this paired sample into? We turned it into a single sample t-test. That's why if you look back at that chart, the formula looks very similar. And when I do it in SPSS, okay, let's open SPSS. When I do it in SPSS, let me find it again. Actually, I think I can just click into it. When I open in SPSS, open, data, and I'm going to go into paired sample t-test. Okay, when I open it up, you'll see again, it kind of, this time does have the data side by side because this is the placebo variable, this is the drug variable. So I'm going to go to Analyze, Compare Means, and in this case, it's a paired sample t-test. So SPSS wants to know what are the two variables that you're pairing, placebo and drug. My option is 95% again. I'm going to say OK, and it'll actually do that calculation for us and give us a t-value, which turns out to be 1.556. Standard deviation turns out to be this. Standard error happens to be that. And the t-score is 1.73. And as it turns out, that represents a significance, a p-value of 0.12, which is bigger than 0.05. So we fail to reject the null hypothesis. The other thing is, take a look at this. The 95% confidence interval of the difference between the placebo and drug is minus 0.5 to plus 3.6. 0 is within that, so it could be no difference. Besides the significance being bigger than 0.05, we can also see that we can't reject because the result, the difference between the two of them, could be 0. The drug may not be doing anything.